In this episode, you'll learn how you can use operational analytics in Azure SQL to optimize your existing databases and applications with no code changes. This week on Data Exposed. Hi, I'm Anna Hoffman, and welcome to this episode of Data Exposed. Today, I'm joined again by Silvano, a program manager on the Azure SQL team. Thanks for joining us again.
Oh, thanks for inviting me, Anna.
Always a pleasure. And today we're going to continue our discussion related to HTAP by talking about analytic workloads and how you can kind of take your existing workloads and applications and databases and optimize them with a few things in Azure SQL. And so before we get into that, Silvano, can you talk us a little bit through the traditional analytics workload and how you make those real time and then how Azure SQL can help?
Yeah, absolutely. So as we have been discussing in our first video, we typically have these two kind of extremes. Our transactional, kind of highly transactional solutions are optimized for inserting, operating, deleting rows, and we want to make this as fast as possible. On the other hand, we want to run those analytical queries, large aggregation scans, and we want to make sure that basically the two can be executed as fast as possible, right? So I have a few slides here where I'm actually starting from kind of this initial situation where our two solutions may be running on two different data stores, right? So we have optimized our transactional application here on the left, and this is highly optimized for, again, the OLTP workload. And in some cases, we are actually transforming, extracting, loading the data into a second system, right? This system is, I'm using Azure Synapse Analytics here as an example, is where we are effectively running our reporting, our dashboarding, our large aggregations, because in this case, this second system is giving us this kind of optimized path for analytical workloads. The problems are here that in some cases we are actually, duplicating data, and this data duplication actually is taking time, right? So is introducing latency between, when the data is inserted in our transactional system until we are able to actually show up the data into our reports and dashboard and such. And there are situations and use cases where, we cannot just afford this luxury, right? We need to be able to execute analytical workloads, reporting, dashboarding on top of the data that we are effectively inserting, right? So here is how we can effectively remove the second system and make sure that we can run our analytical workload directly on our transactional system. And as we were saying in our first video, a technology that is helping us in achieving the best of both workloads is by adding Columnstore indexes on top of our existing schema. So we have this OLTP schema here, which is highly normalized, but we also want to create a Columnstore index. In this case, we will see a non-clustered Columnstore index in order to speed up specific queries, analytical queries that we are going to run. Now, this solution is not for all the different use cases and scenarios. Let's say, for example, our customers have multiple schemas, multiple OLTP solutions, and they want to kind of aggregate data into a common kind of main data warehouse, right? So that's not a situation that we can solve with this approach. But for all those situations, you can imagine, for example, reporting in real time on top of our store sales, right, that are flowing into kind of a very high rate, very high speed. All other situations where we need to do this kind of operational analytics, this is effectively what we can achieve. And we will take a look now in details how we are going to do that, right? So for non-clustered Columnstore indexes, basically what we are doing, we are taking our relational table, which again is optimized for the traditional kind of OLTP workload. And what we are doing here, we are creating this columnar structure on top of the existing kind of relational tables, right? So this means that we are basically duplicating, if you will, a portion of the data, and we are running, and the query processor is good enough to basically detect when accessing those columnar data is actually faster than going through the relational table itself. And the reason why we can keep accommodating our OLTP is because the new data that are inserted, updated, are actually going into this concept of delta row groups, which are basically hosting our newly inserted data until they will reach a certain threshold. And behind the scenes, there are components of our relational engine that are basically taking those rows and are creating a compressed columnar version of the data, right? So this means that we can keep, again, inserting data while we can execute analytical queries in real time on top of the same data. So let's take a look at this quick demo that I prepared here, right? So what we have here, we have a table. This is a order lines table. Let's take a quick look at the size, because I think it's interesting. So right now is around 530 million rows, right? And I have a little application here, which is a simulator that right now keeps inserting lots of new records. I think it's around 2,000 records per second that I'm inserting on top of that particular table. Okay, so if we run an analytical query like this, where I'm grouping on top of this stock item ID, and I'm just calculating a particular aggregation here, you can see this is actually taking quite some time, right? So I'm zooming in here. So this particular query is taking around 3 minutes in order to execute, right? This is clearly not something that we can consider real time. For example, a report or whatever. And this is because we are actually telling the database engine here not to use the Columnstore index that we created on top of that table, right? So if I repeat the same query with side by side here, this time I'm not basically telling the engine not to use it, and I can run the same query. This is the exact same query. We can see is actually taking, in this case, 5 seconds in order to execute, compared to this kind of 3 minutes plus, right? And this can get even better if this kind of query gets executed more and more, right? So this is kind of 2 seconds. So here you can see how, by leveraging this kind of non-clustered Columnstore indexes on top of our OLTP tables, you can run these analytical queries while you are effectively running also the transactional workload on top of your data structures, and basically be faster on both ends, on both the OLTP and the analytical queries.
Wow, that's pretty powerful. And I just wanted to ask a clarifying question here. You talked about how this works, how we kind of duplicate the data in a way to put it in this columnar format. Now, do I have to do anything on my end to kind of restructure my tables so that this will work?
Yeah, no, as I was doing here, I was showing here, the table structure itself is exactly the same as it was previously. So it's, again, a highly normalized data structure where, we are optimizing our data model just for supporting, the OLTP portion. And at the same time, by creating this kind of Columnstore index and non-clustered Columnstore index, we are creating a brand new structure which is highly optimized for analytical queries. And the engine behind the scenes will make sure that those two structures will be kind of kept in sync, right? By adopting this delta store mechanism that I was showing before, new records will pop up in the raw format, still in the non-clustered column store index, until this threshold, which is typically between 100,000 and 1 million rows in the delta store, will be reached. At that point, the tuple mover, which is a component of the SQL Server engine, will kick in and will compress the data and put it in the format which is the best for running analytical queries on top.
Awesome. That's really cool that, basically the engine can take care of all that for us once we set it up, which seems to be pretty easy to set up.
Yeah, absolutely. And as I was describing previously, once we enter into this kind of operational analytical mode, we can actually go one step further, right? So what we have been showing previously was to create this kind of column store index on top of disk-based tables, right? Where data were persisted actually on disks. But we can, again, accelerate even more, especially for the in-memory operations, by creating a column store index on top of our in-memory OLTP table. The way it works here is that in SQL Server and in Azure SQL, we've been introducing this concept of in-memory OLTP tables. This is a new technology that we had a few years ago, where data are actually kept in memory. You can make this persistent or persistent at the metadata only level, or persistent at metadata and data level. But data are in this particular format are really optimized for OLTP. Right? So all the typical structures that in the traditional disk-based tables are basically protecting the integrity of the data, like kind of latches and locks and so on. With this approach, basically we go away, and you can basically speed up the OLTP workload at its best, basically, right? And in memory OLTP tables, we have this particular type of indexes, like hash indexes and range indexes, that are, again, highly optimized for the OLTP workload itself. But now what we can do is we can create, again, with the same approach that we were doing for traditional tables, we can create column store indexes on top of the in-memory tables. So at this point, basically, we can have the maximum speed in driving our OLTP workloads, while we can run analytical queries on top of the same in-memory structures, right? By creating those those two different representations of our in-memory data. The fact that we can guarantee this operational analytics and real-time analytics is because we are not freezing the data in this column store index when we create it, but we can accommodate new data. So the hot data, newly inserted rows or updated rows will keep flowing into the same table. And again, at the same way, we are basically migrating the data from the row store into the tables, into the column store index in traditional tables. We are doing exactly the same here, right? So there is a background task which is migrating our hot rows, the newly inserted rows, from the tail of this in-memory table into the column store in chunks of this 1 million row, right? And we can basically, this slice of our hot data can actually grow. And we do have this compression delay option when we create this column store index that we can use to actually tune when the data are actually not hot anymore, but we want to move it into the column store structures. Like, for example, after 10 minutes or 5 minutes or whatever is our threshold, we consider that data not hot anymore, right? And this is basically, again, without requiring any OLTP application changes, is giving us the best of the two worlds, basically, by giving us the ability to manipulate and OLTP workloads at the best speed, and at the same time run analytical workloads on top of that.
Awesome. This is really cool. I think you also have a demo that you can show us that kind of shows this off.
Yeah, absolutely. Let's take a quick look at this. So I'm gonna close some of these. So in the same exact database, I also had another table here where I'm hosting some kind of IoT data where the locations for a number of vehicles that I'm tracking are flowing into this particular table. I do have also kind of a little generator here, which is inserting actually thousands of new kind of vehicle positions per second. And if we take a look at this kind of this table, it's not extremely huge. It's around 6 million rows. And if I'm doing here, remember our OLTP workload is running behind the scenes. We are now running an aggregation here, so some sort of analytical workload on top of that. This is actually still pretty fast, right? So let's take a look at our query plan here. The query plan itself, the estimated sub-tree cost, as you can see here, is around 10. So pretty fast. This is basically scanning our in-memory OLTP table here. Now let's try to do, as I was suggesting, let's try to create a clustered Columnstore index on top of our in-memory OLTP table. This is going to take a few seconds here. But what we are doing here, we are taking our in-memory OLTP data, and we are creating initially that Columnstore representation of the data. And we will see in a few seconds when this is over how that particular query that where we were aggregating all the rows is going to cost in terms of execution time, right? So in a few seconds, we should be ready to go here. Here we go. So if I'm executing that query again, we can see now what we are doing. We are accessing our Columnstore index. One important point here, if we look at this estimated execution mode, super important now is in batch mode, right? So this means that we are not anymore accessing row by row, but what we are doing, we are loading up a bunch of data and processing the bunch of data at the same time. And if we look at the overall cost here, we can see now is 1.4, right? So this is around kind of 10x faster than how we were running the same exact query before. So here is an example on how, by combining kind of in-memory OLTP tables for OLTP transactional workloads and cluster column stores on top of the same in-memory OLTP, we can get the best of both worlds.
Wow, that's pretty great improvement. And you really didn't have to do a lot. Like you said, you didn't have to change your application. You just kind of added this non-clustered index and you were good to go. That's awesome.
Yeah, absolutely. No application changes whatsoever.
Thanks, Silvano. This has been, a really interesting video to me because you kind of talked us through the capabilities that are present that we have to support this sort of HTAP, and then you stepped us through how we can get performance improvements when we move to in-memory OLTP, and then we move even one step forward to using Columnstore indexes. So this was really interesting. As we think about, what we've seen today, if you were to give a piece of insight or advice to customers who want to start using this, what would you tell them?
Yeah, I think the most important advice is, as we were saying in our previous video, in-memory OLTP tables are actually pretty expensive and pretty scarce in terms of resource. We have in our service tiers business critical and premium service tiers that are actually supporting in-memory OLTP tables. So in case you need this kind of speed, extreme speed in both ingesting data, like for example, in an IoT solution into this in-memory table, make sure that you are selecting the right compute size in terms of supporting your kind of overall data set. And there are techniques that we will talk about on how to offload data from your in-memory OLTP OLTP tables into traditional tables, but make sure that you have this buffer of in-memory tables that is enough to actually contain the amount of fresh data that will come into the system.
Awesome. Thanks, Silvano. That was great advice, and I think a lot of viewers will find it very useful. We have one more video as we kind of talk about HTAP and these different workloads. Can you give us a little sneak peek on what's in the next video?
Yeah, absolutely. The next video is going to talk about, what kind of analytical functions and queries you can actually run on top of this HTAP workloads, and we will see how there's a particular type of capabilities within SQL Server and Azure SQL called window functions that are giving you a very powerful weapon to create analytical queries on your solutions.
Awesome. I am looking forward to it. To our viewers, thanks for joining us today. We hope you liked this video, and we hope you join us next week on Data Exposed.